In some systems, energy is quantized. This means that the system can only have certain amounts of energy rather than having a continuum of energies. Imagine your car only being able to travel for 40 miles per hour, or 50 miles per hour, with no option of the speeds in between. Matter is another example of something that is quantized. Matter exists in packets of atoms or molecules. Energy in some instances can also be quantized, and when describing quantum mechanics, it is necessary. Maxwell's theory on electromagnetism predicted that oscillating electric charges would produce electromagnetic waves. While this could explain where the radiation formed from a black body came from, it could not explain how different objects could produce different spectrums. Using data from various experiments, Max Planck proposed the idea that energy was emitted in portions, or quants. Basically, this equation gives us the intensity of the radiation as a function of wavelength given off at some absolute temperature, meaning that the peak shifts to shorter wavelengths with higher temperatures, and the area underneath the curve increases with temperature also. But really, for our purposes, the important thing to come out of here is Planck's constant. Now, in order to really explain the theory behind his quantum equation, Planck had to make the very important assumption that energy was quantized. Up until now, it was believed that energy existed on a continuous spectrum, just like we find on the macroscale observations. Planck proposed that energy could, in fact, exist as a discrete quantity. This must mean that there was a minimum amount of energy for any given frequency of oscillation, given by his first radiation equation. This also implies that if the energy is greater than the minimum amount given by this equation, then it can only be greater by a factor that is some positive integer of the minimum amount. So energy associated with the oscillations of electrons around an atom is quantized. It is not continuous. Imagine the rungs on a ladder. You can't step in between the rungs. In order to climb the ladder, you have to exert a certain amount of energy and raise your foot to the next rung. We can relate this to Planck's quantum energy by graphing the amount of energy for a given number. The first line represents the absolute minimum amount of energy for a given frequency when n equals 1. The second line represents the amount of energy for n equals 2 at that frequency. Energy can only exist along those lines. Energy cannot exist in between those lines. This theory allowed us to correctly describe the known shape of the black body spectrum and was really the first indication that energy could in fact be quantized. Planck's constant is extremely small, so the difference in energy levels is also extremely small. Really, the difference turns out to be about 0.4 electron volts. While this is significant when we talk about atomic energies, on the macro scale, even if the energies were quantized, they would be too small to notice. So for large objects, quantum mechanics does not produce results that will be indistinguishable from those of classical physics. So Maxwell proposed the idea that all objects emit electromagnetic radiation because of the oscillations of charges within their atoms and molecules. Planck extended the idea to say that the energy associated with these oscillations was quantized and could only be given off in certain amounts. Then Einstein came along and proposed that if the energy is given off in quantized amounts, then the energy of the molecule must decrease by that same quantized amount. We know that a molecule will have a certain amount of energy, and we can represent that energy by NHF. Once the molecule actually oscillates, the molecule will emit electromagnetic radiation in the form of light. The amount of energy carried in that light is quantized and equal to HF. According to the law of conservation of energy, the amount of energy that is lost by the molecule is equal to the amount of energy given off in the form of light. Since the energy is quantized, we can write the new energy as n minus 1 times hf. Using this logic, Einstein proposed that light is given off in discrete packets, or quanta, of energy that are equal to hf. These quanta eventually became known as photons and led to the quantum theory of light.